China's East reactor keeps the fire of magnetic fusion burning. East is a testbed East is a testbed reactor for ITER, an international mega-project in which six countries are working together to build a tokamak to sustain nuclear fusion. East's successes are important for ITER's future because the latter has come under criticism for its delayed timelines and cost overruns. On January 20, Chinese scientists reported that they were able to maintain a plasma at a temperature of 100 million degrees Celsius for about 1066 seconds. January 20, 100 million degrees Celsius. They were able to maintain a plasma at a temperature of 100 million degrees Celsius for about 1066 seconds in a nuclear fusion reactor called the East Experimental Advanced Superconducting Tokamak. In 1938, physicists Hahn and Fritz Strassmann found that energy is produced when nucleus of an atom breaks apart, a process that Meitner and Frisch explained a year later as a process called fission. Only 4 years later, physicists used this principle to build and operate world's first reactor with sustainable nuclear fission reaction. By this time, physicists also knew that energy is also produced when two atomic nuclei fuse together, a process called fusion. The nuclear fission process produces harmful radioactive waste, whereas nuclear fusion doesn't. This is why developing nuclear fusion reactor has become an important technological goal for the world keenly interested in new sources of clean energy. The problem is the amount of energy required to start and sustain a fusion reaction. A nuclear fission reaction can be kicked off by shooting neutrons of suitable energy at the atoms of an unstable nuclei like uranium. For fusion to occur, however, the nuclei need to be exposed to a temperature of at least 100 million degrees Celsius. The lightest nuclei is in nature is of hydrogen consisting of a single proton. An isotope of hydrogen called deuterium has one proton and one neutron in its nucleus. The nucleus of another isotope called tritium has one proton and two neutrons. The deuterium-deuterium fusion requires higher temperature to begin than deuterium-tritium fusion. This is because the extra neutron in the tritium nucleus helps to overcome the repulsion of like charges between the protons. The fusion of a deuterium and a tritium nucleus creates a non-radioactive helium-4 nucleus, a neutron, and 17.6 MeV of energy, which is significant. The neutron can be directed to a blanket of material surrounding the reactor that capture it and release more heat. While deuterium is abundant in seawater, there are no natural deposits of the tritium and it is very hard to produce. At present, it is mostly created by a product in heavy water fission reactors in Canada, India and South Korea. The problem is the amount of energy required to start and sustain a fusion reaction. Nuclear fission reaction can be kicked off by shooting neutrons of suitable energy. For fusion to occur, however, nuclei need to be exposed to a temperature of at least 100 million degrees Celsius. The lightest nucleus in nature is of hydrogen consisting of a single proton. An isotope of hydrogen called the deuterium has one proton and one neutron in its nucleus. The nucleus of another isotope called tritium has one proton and two neutrons. Deuterium-deuterium fusion requires higher temperature to begin than deuterium-tritium fusion. This is because the extra neutron in the tritium nucleus helps overcome the repulsion of like charges between the protons, and the fusion of a deuterium and tritium nucleus creates a non-radioactive helium-4 nucleus. a neutron, and 17.6 megaelectron-volt of energy, which is significant. The neutron can be directed to a blanket of materials surrounding the reactor that capture it and release more heat. While deuterium is abundant in seawater, there is no natural deposits of tritium and it is very hard to produce. At present, it is mostly created as a byproduct in the heavy water fission reactors in Canada, India, and South Korea. The temperature problem, yet another challenge for nuclear fusion, is the temperature. For two nuclei to fuse, two things need to happen, like charges in the nuclei need to overcome, then the particles need to come within 1 femtometer of each other so that they can bond with each other using the strong nuclear force. This force is the strongest fundamental force in nature and responsible for keeping protons and neutrons together in respect of the nuclei of atoms. But on the flip side, it only acts across a very short distance. This is why the nuclei needs to be heated to such high temperatures. I am roughly one-fourth of the width of the carbon nucleus. This is why the nuclei needs to be heated to such high temperatures to give them enough energy to overcome their repulsion and get so close to each other. There are different reactor designs to achieve nuclear fusion. By meeting these conditions, one set of designs involves the use of tokamak, a donut-shaped vessel where nuclei are confined like in a cage and made to fuse. Inside a vessel, a deuterium gas is exposed to about 20 million degrees Celsius. When matter exists in the plasma state, the charged particles are stripped from their respective atoms and float freely. Next, the particles are exposed to very strong magnetic field that acts like an invisible net, trapping the particles along the field lines. This method is called magnetic confinement. Inside the vessel, deuterium gas is exposed to 20 million degrees Celsius. When matter exists in the plasma state, the charged particles are stripped of their respective atoms and float around freely. Next, the particles are exposed to very strong magnetic field that acts like an invisible net, trapping the particles along the field lines. This method is called magnetic confinement. Engineers prefer to use electromagnets, special materials that generate a magnetic field when current is passed through wires coiled around them to create these fields, because field strength only depends on the amount of current in the wires. These wires are also superconducting, that they carry electric current with zero resistance if they are cooled to very low temperatures. Which is achieved by blanketing them with liquid nitrogen or helium. Inside yeast, both toroidal and colloidal magnetic fields are generated by superconducting electromagnetic magnets. It is currently the world's only tokamak which is with this feature. Toroidal magnetic fields around the donut-shaped reactor, while poloidal fields through its center. Together they keep the particles within from drifting into the vessel's walls and collapsing from plasma. Instead, they move in a spiral pattern through the vessel with opportunities to collide with each other and fuse. The poloidal field also induces electric current in the plasma. When parts of the plasma resist the flow of this current, heat is produced, adding up to the energy required to achieve fusion. Through the years, East has been setting a series of records and validating technologies used to achieve them. It was the first to come up to sustain a plasma in a high confinement mode at around 50 to 50 million degrees Celsius for more than 60 seconds in 2016. for more than 100 seconds in 2017. In 2023, East achieved the first steady-state high confinement plasma for 403 seconds, a world record that broke it on January 2025 by sustaining plasma for 1066 seconds. For this achievement, operators provided twice the thermal power to East as they did for the 23 feet, allowing the plasma to remain stable for longer. At present, East isn't producing electricity. In fact, it is yet to reach a milestone called ignition, meaning it doesn't produce enough heat for more fusion reactions to occur, becoming self-sustaining, also known as becoming self-sustaining. To produce usable electricity, a tokamak needs to maintain millions of degrees Celsius for at least few hours. East is a testbed reactor for ITER, an international mega project in which six countries around the world, including India and the European Union, are working together to build a tokamak that will sustain nuclear fusion that releases more energy than that required to sustain the plasma. Crucially, these successes are important for ITR's future because the latter has come under criticism for its delayed timelines and cost overruns. With a bill already upwards of 18 billion euros, ITER has been called the most expensive science experiment in history at a time in which the high cost of doing cutting edge science has put off many governments from pursuing it. Some research groups have also been trying to achieve nuclear fusion using methods that require fewer but still considerable resources. For example, one alternative to achieve magnetic confinement is a device called stellarator, whereas tokamak has a simple donut shape. A stellarator has a more twisting design that is harder to build and operate, but its advantage is that it does away with the need for poloidal magnetic field to achieve a twisting magnetic field inside a vessel. Instead, it achieves the desired field configuration using a more complicated architecture of external magnets. Other designs to do away with magnetic confinement altogether. In one technique, for example, a pellet of deuterium and tritium is hit with a laser beams of extreme power, whereas the deuterium nucleus has proton and one neutron. A tritium nucleon has one proton and two neutrons. When the beams strike pellet, the energy causes the nuclei to compress and fuse, releasing more energy. The heat from the reactions could then be diverted to a pool of water, generating steam that moves a turbine and produces electricity. In 2008, scientists at the Lawrence Livermore National Laboratory in the US began a project called Laser Internal Fusion Energy to test this idea. While they were able to develop lasers with the requisite power, fusion output was found to be much lower than they had predicted. The project was cancelled in 2013 after it became clear it couldn't achieve ignition. But another project at the institute called National Ignition Facility achieved a milestone in 2022. At the NIF, a system of 192 higher power lasers delivered 2.05 megajoules of energy towards a small cylindrical capsule at the center of the room. This capsule, called the Holram, is made of uranium-238 and pelted with gold. It is about 2 mm wide. It contains a thin shell made of polymer inside which deuterium and tritium atoms are placed in frozen or gaseous state. When electromagnetic radiation from the laser enters the hohlraum, it strikes the inner wall and produces X-rays. Over a short span of time, the nuclei are bombarded by X-rays from all directions inside the hohlraum. Eventually, they compress the fuel sample in a symmetric way and heat up rapidly to around 100 million degrees Celsius. In 2022, the NIF said it had used this technique to produce 3.15 megajoules of energy, crossing the break-even point. National Ignition Facility. On the other hand, ITER was launched in 2007 and is expected to produce its first plasma only in 2033, and over time also devour the world's first meager tritium reserves. The desperate need for sources of clean energy means achieving nuclear fusion may just be a matter of time, especially if governments continue to trust the scientists working on the required technologies. Which technology gets it over the line, magnetic, inertial, or something else, remains to be seen. Some private enterprises are also beginning to enter the mix. Researchers discover that old Egyptian remains smell rather nice. If you want to be a global sport, you need to have an event in India. Vijay Amritraj. Thrust on growth, FDIs in Dissanayke's first budget. Anurag Kumara Dissanayke. Now or never for pandemic accord, says WHO chief. Defense training and drone solutions firm Zen Technologies will acquire two firms focused on simulation and related technologies for 130 crore. India-Bangladesh ties should not be regime specific. Bangladesh Foreign Affairs Advisor says India should place restrictions on former Prime Minister Sheikh Hasina to stop her from making public statements that may destabilize situation in his country. Hindus and other minorities are equal citizens, and the government is doing its job of protecting them. Interim government may hold talks with the Adani Group on power project, he says. India-Bangladesh ties should not be regime-specific, Bangladesh Foreign Minister Advisor Tawhid Hussain said on Monday. After holding talks with the External Affairs Minister S. Shankar at the 8th Indian Ocean Conference, he said Prime Minister Narendra Modi and Bangladesh Chief Advisor Mohammad Yunus might finally meet on the sidelines of the BIMSTEC Business Summit in April. One of the concerns India has repeatedly made public is over the violence against minorities, particularly the Hindu community in Bangladesh. Do you think the government has been able to control this? The Hindus or other minority communities that live in Bangladesh are exactly equal citizens with the Muslim or the majority community. They are equal citizens with equal rights or equal rights and equal rights to protection. It is Bangladesh government's job which it is doing to protect them like protecting any other citizen of the country. Unfortunately, just on 5th of August, when Sheikh Hasina, there has been an almost unexpendable frenzy in the Indian media about this issue, mostly based on falsehood. I would invite you to go through the findings in the UN report, which has been published 2 days ago and says the interim government was not involved in the violence. Manipur MLAs get calls in Jay Shah's name, ministerial positions upward. Trump and new glided age for billionaires. Georgia and resurrection of color revolutions. Lighten the population pollution burden of thermal power states. Will build permanent holding areas in up to 60 heavy rust stations. Gyanesh Kumar named CEC after panel meeting. Places of worship case put off center yet to file a response. So that's all for this one. See you in the next.